Hi, and welcome back to the data science course. This is part one, machine learning and data analytics. So in this lecture series, we'll cover regression algorithms, which is a type of supervised learning. We've discussed in the prior lectures both the foundations for building machine learning algorithms, and along with that, in the data science process, we showed how to select the right algorithm. So if you're trying to predict values on a continuous scale, like between 1 to 100, you want 1.27, 3.89, 27.34, and so forth. Then you need a regression algorithm because you're not trying to predict just categories like 0, 1, 2, 3. And as part of that whole data science process, we showed you how to define your different variables. So effectively, if you had a sample, we showed you how you have to split it into a training and a test set, and how to determine which are the dependent or the y values and the independent or the x values, which is x1 to n, which are all the independent variables in the sample which are used to predict the dependent variable y. So if you wanted to predict the stock price, you would take all the different inputs in your sample, like the company information, the market information, the macroeconomic information, and all those variables would then be used to predict the stock price. Some of the most common types of regression algorithms are linear, multiple linear, there's also polynomial. Then we have the tree-based models like random forest and XGBoost. You can use neural networks, and if you remember in the data science process, we explained why we're not covering neural networks in part one of this course. We'll cover it in part two, which is about advanced machine learning techniques. And one of the main reasons is that you need the sample size to be quite large, and quite often it's useful when the output values are difficult to predict. So again, we'll try and minimize the amount of time we spend on teaching about regression again, because as a statistical process, we've already covered it in the statistics chapter. So what we'll do is we'll briefly cover it here again, just to refresh. And if you need to go into some more details, you can always refer back to chapter 3 statistics. So what is regression? So regression is you're trying to predict the output variable, which is your y value, using the input values of the input variables, which is the independent variables x1 to n. So to do that, you're trying to build a linear equation between y and x. So that formula, as you can see here, is given. So y is equal to beta naught plus beta 1 x1 plus beta 2 x2 and so on and so forth to beta n xn plus an error term. So beta is the unknown parameter, or so-called coefficient, for each x. So effectively, if you're trying to build a linear relationship between two variables, most likely there will be some kind of a constant and a coefficient value which determines the relationship between y and x. And the error term is effectively the deviation of the samples from the actuals. So if you remember, again in statistics, we described how to do sampling, what the sample represents in terms of the population, and then how to measure the error terms. So we'll cover that in the error metrics also in this chapter. So this is your typical regression equation. Now to get this value for each coefficient, what we do is that we fit the data. Remember, we've shown you that in the data science process, so you fit the data to the model, and the model in this case is the regression algorithm. So the regression algorithm will learn from the data, determine the values of beta, so they are called beta hat, which is an estimate, to then come up with an estimated value of y. Hence it's called y hat. So beta hat is the estimator for each parameter x1 to xn, and the combined equation will give you an estimate of y, which is called y hat. Now, the difference between y and y hat, so which is the y is the actual value in your sample and y hat is the estimated value. Remember, the model learns from the sample through an iterative process. We showed you that. Remember, with the multiple iterations of the same sample, splitting it into different smaller subsamples, validating that, and at each step it tries to determine the difference between the actuals and the estimate, and then the objective of the whole modeling process, or the objective function, is to minimize the error. We'll use to calculate the estimates for beta hat, and for minimizing the error is the ordinary least squares algorithm. So again, this is something we covered in the regression part of statistics chapter. So what it does is estimates beta hat by minimizing the loss function residual sum of squares. So basically your uh, OLS is the minimization of the RSS, which is the residual sum of squares. So effectively, you take the difference of the errors between the actual and the predicted values of y, square them and sum them. Remember, the reason for squaring is to ensure that the positive and the negative values don't cancel each other out. And then of course remember that the squaring of course increases the order of the calculation, and which impacts the weight given to the outliers. So all those discussions we've already done in statistics and the data science process. So this is just a repeat of that to remind you that effectively you're estimating the values of y based on the sample data. You use multiple iterations of the sample using random samples from the data set given. And what you do is you use a validation set. So for each iteration, you use a separate sample, a separate validation value, check the parameters of the model, and after the end of each iteration, you compare the parameters. And then what you do is, after multiple iterations, you get the best optimized parameter set, which would then give you a minimized RSS. Now, the error terms, or the metrics that are used to measure the accuracy of the model, which is the difference between the predicted and the actual values. These will be also discussed later on this in this lecture. So again, just to briefly mention that, what you're doing is you're trying to find the best fit line if it's a linear model between the data and the predicted values using that data. So, the model is just learning from the data that's been provided. So it knows the input variables, the output variables, and using that it learns from the data to build a model which can accurately predict the output value or the y value for a given set of x values. So if you remember again, geometrically, if you draw a line through your set of points where the line represents the output predicted values, you're trying to minimize the distance between those line points and the actual value. So the line will be through the predicted value points, and there's a scatter plot of the input actual. So we'll show you that now. So you want to get line as close as possible to those values. Just to give you an idea of where more detailed information is available in scikit-learn, we'll show you where the guide is in the scikit-learn website, and it gives you a lot more information about all the different linear regression models, and lots of examples and research papers. You can always read that and improve your understanding of regression. So continuing with this regression lecture, see, this is the same example we used in the statistics lecture. So as you can see, you've got a data set here of inflation and interest rates for 1 year for the US economy, and you're just trying to plot that data. So you're trying to predict the interest rates using the inflation, right? Because normally as the inflation increases, the interest rates tend to increase. So what we did was we just used the actuals, applied the regression model, and predicted the values. So the predicted values are on the red line, all the dots would be inside it, and the actuals are these blue dots. And what the model does is, being this is as a simple linear model of two variables, it's trying to draw best fit linear line equivalent to a straight line equation of y is equal to mx plus c, m being the slope and c being the y-intercept. It tries to get it as close as possible to all the points. Just remember, not just one, but all the points. So what is the best fit line? So it calculates the distance between each of these points to the line, takes the difference, squares it, and finds which is the minimum error term. So the y is the actual, y hat would be the predicted, and then it finds the best fit line. This is a very standard regression technique. You would probably come across that during your regular school or undergrad maths or statistics courses. So this is just a repeat and a refresh of what we've already taught. So you can always go back to the statistics lecture and learn more about this. And just to show you again, the Python code for this example is here. So, we've got that data. We split the data into the independent and dependent variables. We applied the linear regression model. And we'll just show you quickly how this runs, but the actual details and explanation we're going to cover in the next lecture within regression. So we'll explain each and every step properly and in detail so you know how to build a machine learning model using regression or any other algorithm. Especially if you just run this, once it's done, you can see, you got this straight fit line. Okay, so coming back to the lecture, now what we'll do, just mention a few more useful points regarding regression. Again, these have been covered in the statistics chapter. They've been covered in the data science process and in the data wrangling chapter. So if you remember in the data wrangling chapter, we mentioned and across the course that all your machine learning models work on numbers. So if you have text data, true, false, or other categorical text like city names, other groups, these need to be transformed into numbers. We've shown you the techniques and the steps for that in the data wrangling chapter. So you need to encode the data or bin it if it's continuous numeric. And the other thing to remember again is that you don't need to standardize, that is scale, all the data in the regression models. So it depends on the data and the model. If you remember again, most machine learning algorithms require data to be standardized or normalized, which is there being symmetric around the mean with a zero mean and a variance 1. That is your standard normal variable, which defines the population around the mean. Or you have the mean and variance of the same order, but still symmetric around the mean. And the reason for doing that is, again, we mentioned this, that if your model has multiple variables and they are of different scales, it can inaccurately give a higher weight to the variable with a higher scale, right? So 1 to 100 is one variable, 1 to 1 million is a second variable. It's possible it might give a higher weighting to the second variable. So to avoid that, we standardize all the data so that they can be compared equivalently, right? Um, and again, only the training data needs to be standardized, not the test data. The reason for that being, if you standardize the test data, you will get a different mean and variance, and you can't compare the results of the output because, see, the objective is use the sample data to build the model by splitting it into training and test set. So it's the same sample. So when you've calculated the mean and variance, you have to calculate that for the sample. And you've done that with the help of the training set. And that was used to fit and train the model. So all the test data should do is allow you to test the accuracy of the model. Okay. Now, standardization is not done for certain regression models or for other algorithmic models. And these are those models where the size of the feature doesn't matter. And that's because they're not distance based, they are condition based. So what you do is you build a tree with multiple levels or nodes, and you take a decision at each node using multiple input variables as conditions. So the value of that individual variable or condition wouldn't matter, correct? Well, we'll show you this when we discuss the decision tree models. So for now, it should be sufficient to understand why and how you need to standardize the data. And one last thing to mention is that within supervised learning algorithms and even in other algorithms, you'll find that quite often the model will underfit or overfit the data. And that depends on the data size and the complexity of the model. There is a way to solve this problem by using the bias variance trade-off, and we'll discuss this further in the lecture. Just to remind you again, where all the data and Python code examples are available for the regression algorithms and generally for the course, it's the same GitHub location. Let's just have a look at that again. So that's the GitHub location. If you go into the examples directory and look at the regression chapter, you will see all the sample Python code there. And we'll of course discuss these for each of the individual models when we show you how to build them. And the data is in the same data folder. You've got all the data for all the Python code examples for the entire lecture series here. And we'll be using a couple of these files. So we'll point out what these files are. Okay, so now let's look at the bias variance trade-off issue. So, so we mentioned that there's this problem of overfitting and underfitting of the model to the data. And what that results in is that the model gives you good results with the training data. So you'll get some high accuracy measures in terms of your error metrics. But what happens is when you test it using the test data, it'll give you bad results and the metrics will be poor. So that happens when either your model is too complex or your training data size is insufficient. So it could be small or large depending on the complexity of the model. So these two things impact the overfitting and underfitting of the model to the data. So let's understand the bias and variance terms. So bias is effectively the underfitting of the model to the data. And it is the error when the estimator makes assumptions about the model from this training data rather than learning from it. So it's assumed certain things from the data rather than using the data to learn the behavior of the entire sample. So basically, it's underfit to the data, and that happens due to less data. So slightly confusing, but what's happened is the amount of sample data is too small for the model. So what it does is actually remembers the entire sample, the entire data set, rather than using the data set to learn from it. And as a consequence of that, you will get a model which will work only for that data set because it's only used that data set as its source to fit the data. And if you now give it a new data set to test against or a completely new data set to predict values from, they could be very different from the training data. So the output results would be very different and hence the model would fail. So this is the case of underfitting or bias. Uh, and underfitting occurs when the model has a high bias and a low variance. So effectively, the model has been impacted by the bias in the learning process, and that is occurring because of the less amount of data. And as you can see, the low bias estimators, they would make less assumptions about the model, and high bias estimators would make more assumptions about the model. So remember this estimator and model term we'd explained in the data science process also. So the model is any algorithm that you're building, be it regression, classification, and within scikit-learn, the terminology is called estimator, which is the object of that model class. So each algorithm or model is a class. So when you instantiate that, you create the object. And so that's your estimator, which is then used for learning from the data and building your actual algorithm. Now, what is variance? So variance is actually the inverse of the bias factor. So it's overfitting to the data. Now, this happens when the estimator is learning too much from the data, and that generally happens when you have too much data. So, if you remember when we discussed in statistics, if you have a very large sample, it gets closer and closer to the population, right? Uh, but now imagine that if you have a large population, most likely some of the data in that would be erroneous or just noise. It's not relevant. And that's what is happening here in this case. So the model has learned from the training data to such an extent that even the noise in it is being used for predicting the values. Now imagine if you had a large sample, it gets closer and closer to the population, and the population would of course have all the variations, including the noise and the error. You don't want to train the model on that because if the input data has even the slightest variations, you'll get a completely different output, which is most likely erroneous. So you don't want such a bad predicting model. And once again, the low variance estimators are less sensitive to the training data, And the high variance estimators are more sensitive to the training data because that's how you build the model. So you want to minimize the impact of this sensitivity to the variations in the data. Now, if you consider the data science process that we discussed, we want a good model which can, as accurately as possible, predict the output for new data sets. So effectively, you want a model that has low bias and low variance, right? So irrespective of the model or the data, you want a good output which takes care of this underfitting and overfitting of the model and the data. And the way to do that is by using the bias variance trade-off. So there's a very useful and good research paper which is published by Scott Fortman Rowe. You can search it online, it's very easy to find. And there they explained the bias variance trade-off, and it can be shown here nicely in this form of a graph. And it shows the inverse relationship between bias and variance. So as the model's complexity increases, your variance increases and your bias reduces. And vice versa, as the complexity reduces, your variance reduces, but your bias increases. And just be sure that you can see that the error is high for both high bias and high variance. So you want to reduce the error, so you would go for a lower variance and a bias, and a model which is less complex. So there will be a trade-off. And that's what the whole bias variance trade-off is about. And if you remember the data science process lecture, we'd explained what the way is to select the right model based on the data and the problem that you're trying to solve. And the best way to do that is to select linear models for linear problems and non-linear models for non-linear problems. And you can see enough examples for that during the lectures which we teach from here on. And what you will find is that generally the linear models like linear regression will work well for simple linear problems. And non-linear models like decision trees and random forest are good for solving non-linear problems. We've shown you some rationale for deciding on the algorithms during the data science process. Now, if you remember, as part of the data science process, what we'd also shown you was how to use the k-fold cross-validation to use multiple subsets of the training data in multiple variations, in iterations to build the models iteratively, optimizing the parameters by hypertuning them. And this is where you can optimize the bias variance trade-off. So as you remember here in this lecture, you've seen that the bias variance is caused by the model complexity and the size of the data and the way it learns from it. So by doing multiple random sampling of the training data, you're able to eliminate some of the impact of bias and variance. And if you choose the right model based on the data size, then you can incorporate some of the abilities of the model to handle the impact of bias and variance. So if you have a large data set, yes, you can use neural networks. But if you're trying to use neural networks for a small data set, then most likely you will see the impact of bias and variance. Because it's a complex model with a small data size, it'll most likely give you inaccurate results. But again, that depends on the problem and the data size. Okay, now the final part of this introduction lecture for regression is the error metrics. So we've already explained these terms as part of the statistics lecture because regression uses these error terms and we are building regression models here. But we'll discuss them again just to make sure that you understand that these are the error metrics used by the regression algorithms when measuring the accuracy of the models. So what are they? So one is MSE or the mean squared error, which is the most common one used, and it's basically the average of the sum of squares of the errors. So if you remember again, as part of the regression model, you're predicting the values of the dependent variable y, the y hat value, and the equivalent value, which is the actual value, is in the sample, which is y. So for each such y, you have a y hat, you take their differences, square them up, and sum them up. Now, the reason for squaring the difference is that you don't want the positive and the negative values to cancel each other out. So we've already explained this. Basically, if the estimated value is greater or smaller than the actual, you'll get a positive negative value. So by squaring it, you remove the impact of cancellations, and then you sum it up. Now this of course has its own side effect. So because you've squared the error, the higher the error, the more its impact on the final MSE value, and that means it's a higher impact of outliers. So you need to minimize that too. And of course, the closer the MSE is to zero, the better it is for us. The RMSE is just the square root of the MSE, and the reason RMSE is more useful is because it's of the same order as the data. So see, the MSE has been squared. So if your data was of the unit or order x, MSE becomes x square, whereas RMSE is of the same order as the data. So it's more preferable to MSE. That too would of course be impacted by the size of the outliers, but you can at least compare it in a more equivalent way to the data. And of course, the closer it is to zero, the better. Another useful measure for error metrics is the MAE, or the mean absolute error, and it is the average of the absolute difference between the predicted and actual values. So all you've done again is you've taken the differences between the actual and the predicted values for the dependent variable y, taken the absolute of each of those values. So absolute is, remember, in basic mathematics, it gives you the positive value. So even if you had -2, it will give you 2. If you had 3, it will give you 3. So what it's done is, just like squaring, it's removed the impact of cancellation of positive and negative values. So it's incorporating the impact of each error term by simply taking the absolute, and then you average it out. Now, the uh, side effect of this is the opposite of what you saw in MSE and RMSE, which is that the impact of the outliers is not as high as it was in MSE or RMSE, and that's because you haven't squared the difference value. Now, if you wanted to identify the impact of the outliers on the model, then you won't be able to use this error metric. So again, depending on the data and the model, you can easily select any of these error metrics, and there are a lot more error metrics which you can use. So we'll now discuss the last error metric in this lecture, which is R square, or the coefficient of determination or goodness of fit. So what it does is it explains how well the model fits the sample. So the MSC, RMSC, MAE will tell you what is the error, how big it is, what is the impact of the outliers. But how do you know how well the model fits the sample? So you use the R square value, and the formula for that is 1 minus RSS by TSS. RSS, we explained, is the residual sum of squares. So difference of the actual and predicted square sum. Similarly, the total sum of squares now is the actual average. So you've got the actual values of the dependent variable y. If you took its actual average for all those dependent variables in your sample, and now you subtracted that from the individual y values. Remember what that was? If you remember the statistics lecture, it was the variance of the dependent variable or the y variable. So the RSS is giving you the variance of the model's prediction, and the TSS is giving you the variance of the dependent variable. So the R square is then measuring how well the model fits the sample. That is, what proportion of the variance in your dependent variable is predicted from the independent variables, right? See, again, right, this is all coming down to the fact that you want to minimize the variance, you want to minimize the bias, and you want to get a good fitting model which can explain the results, which are of course dependent on the input or the independent variables. And the closer it is to one, the better the estimate. As you can see, you want to minimize this ratio, so you get as close as possible to one is the best number for R square. Now let's look at the scikit-learn guide to see what all other different regression metrics are available which you can use. You can see there's a host of metrics available. It's given you examples, so you can easily select which is the best one for you based on the model you selected and the sample size. Okay, so with that, we'll end the introduction to the regression lecture series. Hopefully, you have all the foundations for building the models by now. You can write Python code, use pandas, understand the statistics probability, you understood the data science process, and now we are doing the most interesting and exciting part of the course, which is building the algorithmic models, and the first one being regression. So once again, thank you for joining the course, and see you in the next lecture. Thank you.